Hello, welcome to this Docker course. I'm going to show you the base for modern applications, although these applications typically are cloud applications. According to Docker authors, Docker is an open platform, meaning it's open source, for developing, which helps you develop your applications, shipping, helping you share your applications in a uniform way, and run applications, specifically for system administrator to be able to manage in a uniform way any application, because the applications will be packaged with all its dependencies, including the operating system, into a standardized unit of software development. This might look like a bit at the beginning as virtual machines, but let me explain the difference between virtual machine architecture and the containerization architecture. In a virtual machine architecture, you might want to have different virtual machines for your different applications, but this means that you have to spend resources such as memory and time on each guest operating system in order to run your application. So to run your first application, you have to spend some memory, some time in order for that operating system to start, and then you can start your application. Then for the second, for the third, and so on. Whereas in a containerized approach, the operating system is only used by the engine. Then the engine provides all the support for these containers to run. So when a container needs to start, because it's already containing all its dependencies on all its files at the starting stage, it can start immediately. Let's talk about terminology. An image is the content at rest, particularly the content of your disk at the starting stage of your application. This content is all the binaries, including those from the operating system, those from dependencies, as well as resources, data, files that you might need. It also contains configuration parameters. We will look into those configuration parameters later. A container is the standard unit for an application or a service. The container is the image when it's running. So it's its own environment which starts, it's initialized by the content of the image. If we want to change something, because the images are static, we need volumes. The volumes are configured within the container to allow different files within the file system to be edited and to persist through restart cycles. The engine, as we have seen, is the software component that allows the containerization of our applications. The registry is an image management, so that it enables the storage and distribution of the images, so that we can share these images or we can download images from a registry. And the control plane is the component for us to control the engine, to start containers, to see the status of containers, and so on. We have we can have different control planes, such as command line interface, or applications such as the Portainer application for controlling our Docker. So let's see how we can start with Docker. Very simply, we can run a container with Docker run and then the name of the image that we want to run. In this case, we want to run hello world, so we ask the engine to run hello world. The first thing that the engine will do is to see if it has that image, in this case hello world, locally. If not, then it will automatically pull this image from a registry. Generally, this registry will be the Docker Hub registry, which is the centralized registry for all Docker. Once it's downloaded the image, it will create the container and put the file system according to the image into that container. It will configure all the configuration parameters for that container that are by default in the image. If not, we can also edit that configuration in the runtime. But typically what we want is, as developers, create our own images. For this we have to create the Docker file, which I will show you later how it looks, and then we want to build that image with this command, docker build the current image and tag it with this name. So once we build, or once we start building this image, the engine will look for images to build our image. Once we have our image, we can run this image, and once we've checked that this image is working as it's supposed to do, we can then push this image into our registry, so that other nodes or other partners or other computers can pull that image and run it by themselves. Let's look at what a Docker file is. First, we need the directive of from. This means that we can build our image based upon another image, such as an operating system or a common framework or whatever there is. I suggest to look into the available images in Docker Hub to get an idea of that. But typically you want Ubuntu, Alpine as operating systems, or you want JDK for Java applications, or you want Node.js for Node applications. So you can start already from an existing image. Then you might want to copy your files into that image. This meaning copying your binaries and copying your data files into that image. You might want to send some environment variables by default. If not, they can be edited in the run command. Then we want to specify, or we might want to specify the entry point. This is configuring the console or the main program that will be used when the image is run, so that we can, when we run, we can add parameters. If this is the case, those parameters will be added to the entry point. We can define the ports that will or could be export. We can define the volumes that we are going to use and in which path these volumes typically will be configured. We might want to run some commands within this image while we are building the image, for example, to install some dependencies or install some libraries or whatever we need, or change the permissions on a file or whatever it's needed to configure our image so that it's at that running state. And finally, we specify which is the command that will spark the start of our application. How are images built? Typically, or absolutely, every image is identified by its own hash. This hash is then tagged by a name which is optionally the server. If not, this is assumed to be Docker Hub again, by a group which is optional, but typically to separate different images we want to group them. By the name of the image, of course, we want to, this is mandatory, we have to give our image a name when we tag it, and optionally a version. If we don't put a version, either by building or by calling it, latest will be the default value for version. Each directive that we've seen before will create its own image, and in the sense of a hash image. In this way, the images are built very similar to the commits in a Git. So, for example, if we want to build our image for an application and we start with the directive from Alpine, we have the image Alpine, then we want to install some dependencies, then we want to copy an application, and then we tag this image as application 01. this is one image, this is a second image based on that image with its own hash, this is a third image based on this image with its own hash. So when we need to create a second application, we already have this image. So the Docker engine doesn't have to build completely this image again, it can just reuse it, and this is also the case for most of our applications. So even though our image initially might be scary in size because it's in the order of gigabytes, let's be sure that when we have many images, most of it will be reused, so we are saving space in our hard drive. Let's look at the use cases for Docker. The first and most basic use case is to run a single application. We already know how to start and stop a standard application. This is standard individually of the technology the application is going to be written in. Me, as a system administrator, I use Docker run to run this image in its own container, and it starts that application. If I want to stop it, I just say Docker stop the container, and it stops the container. We can provide persistency through volumes, so we have different volumes for this container, and we have networking for this container. We say, okay, expose this port to the outside world so we can access this application. So now that we know how to use and deploy a single application, let's say that we want to replicate this application. We have exactly the same application running twice. We might want this for scaling our usage or for having testing versus production. We can have one application in production, the other application for testing. It's running the same code because they're using the same image, and the only difference is one is running on port 1, the other is running on another port, so we can access our different environments standard way. This might not be as easy without Docker, because depending on your technology you have to build your environments, and even replicating environments might be difficult. One cool thing is that we have the same volume mounted on the different containers, and this is also a possibility. We can run the same application on different versions on the same host. This might be useful in examples for databases. Let's say I have an application that depends on MySQL version 1.1 and another application that is more updated and it is dependent on MySQL version 5. I can have both MySQLs running, of course, on different ports, on the same port, as I'll show you shortly, so that the other applications that I'm running in my Docker can access the correct version. I've already hinted at this. How can we create applications based on microservices? So I can have an application or a service in a container, such as the MySQL, which is being used by another application, such as a web application. In this scenario, we might want to have internal networks, and indeed Docker offers you the possibility to manage networks, virtual networks. Every container pertaining to a network can see the other containers in that network. So even though this container is a container and is exposing a port, this port is available for this container, but because we have not exposed this port, it's not available outside this network. This container and this container may be exposed in the same port, but because they are acting as their own node, we can still use them in their native port. Of course, this will be a problem if we want to export the same port outside our host, because our host can only export one application per port. One last thing in managed networks or internal networks is that every component, every container in this network can see the other containers in that network through a DNS, and this DNS can be configured. By default is the container name. So container A can access container C just by using C. It doesn't have to know the IP address that Docker will provide it. What if we want to compose, so we want to standardize these ways of microservice management or microservice architecture for our applications? Then we have the Docker Compose. In the Docker Compose, we define services, which are the containers. So you can see services as an application. We can define the export pods, we can define the volumes that can be shared across the different components, we define common variables, and we define the networks. This is how a Docker Compose looks. It's a YAML file. We say the version, the services that are running, in this case is web service and the Redis service. In the case of the Redis service is specifying the image for that container. This will be transformed in a container. In the case of web, the ports are explained, the volumes that are going to be used is explained, and other parameters and the dependencies are also explained there. We have global volume that is also being used in the volumes. So finally, what if we want the concept of an internal network to be shared across different hosts, different nodes? Then in this case we want to look into orchestration. This is a pretty advanced concept that is best to know once you are familiar with the standard Docker philosophy. For this, the most used orchestrating software is Docker Swarm, which is a mode for our Docker, and Kubernetes, which also uses the Docker standard for this. So essentially, the idea is that we might want to have our application distributed in different nodes. We might want our containers, our services to be replicated in case one of them stops for whatever reason. We might want to have them replicated in different nodes. We have one in node B and the same one in node C in case a whole node fails. And we might want to have them for when we need additional instances because our load is spiking. So actually Kubernetes is able to manage this, control all the parameters of the containers, and decide whether you need new instances of your containers or not. There are even in this category, there are even components of Kubernetes that will help you analyze the communication between the components, not only across the nodes, but within your internal network, which kind of calls are being done. It will analyze the memory used, it will optimize your deployment. So this is for high-end application provision, but it's based on this very simple concept of containerization of our applications. Hope you have learned something for today, and see you